Welcome back, everyone. In this video, I will be continuing the section on max and min values. In the previous video, at the end, we defined what critical numbers are. And critical numbers are the numbers where our derivative equals 0 or does not exist. So what we're going to go ahead and do is compute the critical numbers of a couple functions here. One thing I want to go ahead and say is about these functions, most of the time we're dealing with figuring out critical numbers are functions relatively simple, meaning it's usually something like a polynomial or something times e to the x like this, and occasionally we'll have a fraction. So these are really two of the three main types. Now you can of course see other things, but the main thing is when we set equal to 0 to solve, as we know we have to do for critical numbers, you have to actually be able to solve it. So your function won't be incredibly messy. All right, find the critical numbers. First thing to do, we need the derivative. And for this one, we know we're going to have to use the product rule because we're multiplying functions here. The derivative of x cubed is 3x squared. The derivative of the first times the second, which is just e to the negative 8x, plus the first, plus x cubed, times the derivative of e to the negative 8x would be e to the negative 8x. Then the chain rule says multiply by the derivative of the exponent, which is negative 8. Now, one thing that we outlined in the steps to finding the critical numbers is you don't just compute the derivative, you need to simplify it. Now, at this point, when we say simplifying, we're not setting it equal to anything yet or solving anything, so you don't cancel anything out, unless if it's like a 2 minus a 2, of course, we can cancel that out. But we just want to be able to really factor. And when we were computing derivatives, we really talked about factoring quite a bit because we want it to be second nature now. So if you're thinking about factoring out in this problem, we have an e to the negative 8x in each part, which we can factor out. And we have an x cubed and an x squared. Notice that the numbers here, 3 and negative 8, have nothing to do with each other. They don't have a common factor, so we can't do anything. But we can take out the smaller power of x, which is x squared. And then we can take out the entire e to the negative 8x because it matches exactly. And this is what we're going to factor out. And this just helps immensely when you do the next part. I promise you that. If you don't factor simplify before you find the critical values, it takes a lot longer. So just go ahead and factor out, simplify. So we take out the x squared, we take out the e to the negative 8x. What are we left with? Well, in the first term right here, all that's left is 3 because this entire part has gone out. And now what are we left with in the second part? Well, the entire e part is gone. We took 2 of the 3 x's there, so there's just an x times negative 8, which is minus 8x. This is the simplified derivative. And by simplified in this manner, we mean factored. That's in general what we mean is factored because we do not have any, how should I say this? We don't have any fractions here. There's nothing really additional to do. Now, one thing you can concern yourself with is something I talked about before with negative exponents. But when we're talking about negative exponents in problems, we mean x to a negative exponent. If x is in the exponent itself, it doesn't matter if you have an 8 or a negative 8 here. It can be positive, it can be negative. So you don't want to bring this down to the bottom. All you're going to do is make it more complicated. With the next one, maybe we'll see with the fraction here. Maybe if we do it a different way, a wrong way, we would end up with a negative exponent. For this one, just repeating what I just said, we only care about getting rid of negative exponents if the exponent is just a number. If you have x in the exponent as well, just leave it alone. All right, so what do we want to do? Well, one thing is we want to solve where f prime of x equals 0. And that's all we're actually going to have to do here because we don't have a fraction. But let's focus on just doing this one first. So we have our derivative here, x squared times e to the negative 8x times 3 minus 8x equals 0. And then we want to go ahead and solve this. Well, the reason why factoring out helps out so much is because it's already factored, we can just set each part with x equal to 0. So we have x squared here, set it equal to 0. We have e to the negative 8x, set that equal to 0. And we have 3 minus 8x. We also need to set that equal to 0. Now, all of these are problems that you should be very comfortable solving. Now I might use shortcuts that you're not familiar with or it's just been a while, but I am going to use them because it just helps so much when we go through full length problems to know how to do these shortcuts that you should have seen before. So anytime we have x raised to a power equals 0, that just means x equals 0. Because if something raised to a power equals 0, that means when you multiply it by itself, it's got to be 0. Well, the only possibility is if it's 0 itself. And the one on the right here, this is straightforward. We would add the 8x and divide by the 3. So quickly we would get x equals 3 over 8. Now what I want to go ahead and do is with this middle one, you probably have seen a shortcut with it before, but I wanted to describe it very specifically. If we wanted to solve this from scratch, we did a lot in the exponential growth and decay, solving things like this. We do the natural log of each side to get rid of the 8, and get rid of the e, and we have negative 8x, the exponent equals the natural log of 0. Well, what happens here is that the natural log of 0 is undefined. This does not exist. Now, one thing I don't want to cause confusion is we're not saying that the derivative does not exist for this problem. What we're saying right here, we're saying that this specific equation, negative 8x equals the natural log of 0, this number does not exist, which means this original one has no solution. Since negative 8x equals a number that does not exist, if you divide by negative 8, it still does not exist. And one thing that's important, and I'm going to go ahead and write on the side, is that e to anything, so it could be any equation at all, it could be e to absolutely anything at all, equals 0 is always no solution. And that's just because the graph of e, or the graph of any exponential function, it never equals 0 because you have that horizontal asymptote. So maybe if I just put f of x, actually we're using that for the problem, but what I'm saying here is you could have any function up here at all. This time we have negative 8x, you could have x squared plus 1, you can have literally anything. You can have cosines, sines. If you have e to the something equals 0, there's no solutions. So for the purposes of what we're doing here, I'm just going to cross this out. And in the future, if e to the something equals 0 comes up, I know I can just X it out. No solutions. Well, what we've figured out here is that at least based on where we're at this point, we have two critical numbers. We have 0 and we have 8. And I'm going to kind of record them on the bottom here. We have 0 and we have 3 over 8. Now we technically have two more things to do when we find critical numbers. We need to solve where f prime of x is d and e. Well, I think I'm pretty sure I outlined it in the previous video, but just to reiterate, solving this is very weird to say, but really what you're looking for is if there's a fraction, you set the denominator equal to 0 and solve. Well, the main thing is there's no fraction here. We could have made one from the e to the negative 8x by bringing it to the bottom, but then we would just be solving e to the 8x equals 0. So that's why that really doesn't matter. But the main point here is that we have no negative exponents. We have no negative exponents. That means there's no hidden fractions here in our derivative, and therefore there's nothing to solve here. So nothing to do. There's no fraction. So there's nothing to add in there. For f prime of x is d and e. That means the last thing we have to do is make sure that 0, the two critical numbers we have so far, 0 and positive 3 over 8, are in the domain of f. Well, this is going back to pretty much one of the very first sections we did in this course, but we talked about really the three things that you can't have that will restrict your domain. You cannot have radicals. Well, we don't have any radicals here because we don't have any fractional exponents. You cannot have logarithms. Well, we don't have any logarithms, so that's not a problem. And you can't have any denominators. Well, that's not a problem either. This means the domain of this is all real. All real numbers. Okay, no matter what we plug in, because we don't have those three restrictions, there is no restriction on the domain. So since the domain is negative infinity to infinity, they both are critical numbers. All right, and I'll just go ahead and write down what I said on the side here to check the domain since it's been a while. Remember that the domain of the natural log of x is has the condition that x has to be greater than 0. So if you have a natural log anywhere in your function, you have to solve where is x greater than 0. If you have an even root radical, so the even root n of x has to be greater than or equal to 0. No even root radicals. And then the last thing is denominators. And we know in general denominators cannot equal 0, but we have no denominators either in our original function. So because we don't have any of these three problems, we don't really need to do anything more than just say we found our critical numbers. Now in general, most functions that we're going to be dealing with have domain of all real numbers, which means that you don't really have to check because things like polynomials automatically have domain of all real numbers, and those are easier to deal with. What we just did though really was an absolute full throttle. We did everything we could possibly check here. We did the derivative, we simplified it, we set it equal to 0 and solved that. Those are really the normal steps. The extra steps, if you have any issues like a fraction in your derivative formula, or pretty much just a fraction, then you have to set the denominator equal to 0. You might get some extra stuff. And then you also need to figure out the domain of your function and see if they work. But in this one, we just kind of talked. We didn't have any of these three problems, so there's no issue for the original function. All right, well, let's go ahead and work number 2 here. Number 2, we can already see we have a fraction, so there will be a restriction on our domain, but we don't really need to worry about it until we get our possible critical numbers and check. Just put a line here to separate. We want to find the critical numbers of g of z equals z minus 1 over z squared minus 3z plus 3. Right, well, without any more thought, we know we need to do the derivative, and we have a fraction here, so there's going to be the quotient rule. The derivative of the top is 1, and we multiply it by the bottom, z squared minus 3z plus 3. Then we subtract. We have the top, z minus 1, and we multiply it by the derivative of the bottom, which is 2z minus 3. Once again, the hope is because we've gone through all those derivative rules and done so many examples that you should be comfortable with this. And then we're dividing by the entire bottom, z squared plus minus 3z plus 3 squared. All right, well, what we've really got to do when we go through and do this is simplify. And we know what it means to simplify when it comes to a quotient rule is simplify the numerator. And then if you can go any further after simplifying the numerator, try to do that. But if you cannot, then that's it. All right, so the first thing here, distributing the 1 does nothing. So we got just the z squared minus 3z plus 3. And the back part here, you want to FOIL. One thing you want to point out here is because this minus sign is right here, I like to just do a minus because I don't like to do everything at once. And whatever you FOIL out, just put in this big parentheses. Okay, so z times 2z is 2z squared. Z times minus 3 is minus 3z. Minus 1 times 2z is minus 2z. And minus 1 times minus 3 is plus 3. And we're just going to keep simplifying. You can see this one's kind of much longer derivative than the other one, but it's mainly the simplification process. So I'm going to rewrite the denominator like I always do with the quotient rule. And then the numerator, well, we can just go ahead and simplify a little bit as we go. We have z squared minus 2z squared, which would be minus z squared. We have one of them we're taking up 2. Then with the z's, we have negative 3z minus, and then we have minus 3z minus 2z. Well, this is minus 5z. So I'll go ahead and write that inside. If we're doing negative 3z minus negative 5z, that's really a plus. So negative 3 plus 5 is 2. So we get positive 2z. And once again, just take as many steps as you need if you need to spell it out a little more. And then finally, we have 3 minus 3. Well, that one's actually pretty nice because that's just 0. You can write 0 or just realize that they cancel out and we don't need them at all. All right. So are we done? Well, we're pretty much done, but we can do one thing to factor on the numerator. And we know because this is a fraction, we're going to set the top equal to 0 and the bottom equal to 0 separately. So we're going to go ahead and factor the z out here. When you take a z out of the numerator, you get negative z plus 2. And then that's over the bottom, z squared minus 3z plus 3 squared. Now you can ask the question here, does the denominator factor? And your answer, you can actually go through the options. It is no, because we would need two numbers that multiply to positive 3 and add to negative 3. And there aren't any at least nice numbers. So we can't factor this, which means it's not going to cancel with anything up here. Right, now, because this one's a fraction, I'm going to really consolidate the two steps 2 and 3 into one. We're going to find the critical numbers. And the way we're going to do that is with two things. We're going to set the numerator equal to 0 and solve that. So we got z times negative z plus 2 equals 0. And then we're also going to set the denominator equal to 0 and solve. And that would be this entire thing, z squared minus 3z plus 3 squared equals 0. Right. I'm going to do the first one first, the numerator first, because there's something special going on with the second one, and I don't want to talk about that before we do the first one. Now, solving the first one is not going to be bad at all because it's already factored. It's just single powers of z. Set each part equals to 0. We got 0 equals 0. Well, that's already done for us. And negative z plus 2 equals 0. Well, you just add the z to each side here and you get z equals 2. And so we do have two possible critical numbers here. We'd have to make sure they're in the domain. But one thing I want to mention is that the domain of this function, the original function, I can kind of write it in words because we know we have a fraction here, so we can't use when the denominator equals 0. So it's all real numbers except when z squared minus 3z plus 3 equals 0, or when the denominator equals 0. Now the reason I'm bringing that up is twofold. One, if we plug in our z values here, we would see if we get 0 or not, so that means we would keep them or throw them away. But the other thing that's more useful right now is that when we're solving this, so the one that where the denominator equals 0, notice we're solving the same thing because we have that squared there. If we want to set the denominator equals 0, which is this, and solve it, we would do the square root of each side would be the first step to get rid of that squared. Now, technically, you have a plus or minus, but the square root of 0 is 0. So when you do that, you're just down to z squared minus 3z plus 3 equals 0. And remember, we're solving for a critical value here. Well, we're solving for a critical value, but we're going to throw away anything that breaks this. Anything that satisfies z squared minus 3z plus 3 equals 0 are not actually going to be included. And that's the same equation here. So what's going on is since this matches the equation of the numbers not in the domain, that means that when we solve this, if we get any numbers from solving this, they can't be critical values. They cannot be critical values. All right, so just think about that very quickly. We did our derivative. When we got the derivative here and simplified it, when we set the denominator equals 0, it was pretty much the same denominator as the original, except squared. Well, when we set that equal to 0 and solve it and start by doing the square root, then we're actually solving the same equation as the domain. Well, let's just pretend the number here, if we solve this, we get z equals 1. What that's saying is 1 would not be in the domain of our original function. But when we solve this, we would get 1 because it's the same exact equation. And since 1 is not in the domain, it cannot be a critical value. But what I'm trying to say here is that if the denominator of your derivative matches the denominator of the original, like this one does. Yes, we have a squared, but we saw that it basically doesn't mean anything when it comes to computing this. What we just figured out is that we don't have to solve this. So what this is saying is no critical values from this. Okay. So hopefully that makes sense. Just think about it. What I'm going to go ahead and do after we establish that whether these are critical numbers or not, the 0 and the 2, is I'll show you with the graph how this is all working, why this all makes sense. All right, so the last thing you really got to do is verify, make sure that these do not make the denominator equal 0. And you can just do that by plugging them in. So what we need is 0 in the domain and is 2 in the domain. Well, all we got to do is plug it into the denominator and make sure it doesn't equal 0. So what happens if we plug it into the original denominator? We get 0 squared minus 3 times 0 plus 3, which equals 3. That means, yes, 0 is in the denominator, or sorry, 0 is in the domain. And then what about 2? We get 2 squared minus 3 times 2 plus 3. What does that equal? Well, this is 4 minus 6 is negative 2 plus 3 is 1. And that's also not 0. That means they're both in the domain. And that means these are both critical numbers. Once again, I'm going through these examples in all the possible details so you can see everything. For the most part, there will be some times that it can trip you up, but if you do the derivative, simplify, set it each the top and bottom equal to 0, and you get those numbers, they almost always work. But to be complete, you have to make sure they're actually in the domain. So here our critical numbers for this problem are just 0 and 2. Okay. So like I said, what I want to go ahead and do is just show you what this graph looks like. And we can see that these are kind of the only two critical numbers. But I'm going to go ahead and bring over Desmos. Let me go ahead and actually put it right here so I can type it in first. I'm going to use y's and x's. So y equals x minus 1 divided by x squared minus 3x plus 3. And I get this graph here. I'll kind of zoom in a little bit. But what we have as far as our problem is we figured out the only critical numbers are x equals 0, which is right there, and x equals 2, which is right here. In order for the denominator to be 0, or it does not exist, we've actually learned that that's vertical asymptotes. Well, regardless if it's actually 0 or not, what's happening here is that there is no vertical asymptote. So even if you went ahead and solved this denominator equal to 0, you actually would not get an answer. You would get an imaginary number if you solved this. So really the domain of our original function was all real numbers because the only issue, this possibly equaling 0, cannot actually equal 0. And when we go through and solve, all the numbers we got would have been our critical numbers, which are the 0 and 2. But you can also see they're the critical numbers. 0 is a little bit harder, but this is a minimum because if you look at the y values to the left, they're a little bit above. So notice that's negative 0.333 at 0. And if you go and move, it's above negative 0.33. And if you go to the right, it's a little more easier to see to the right that it's going up. And then at 2, it's going down because, well, that one's just easier to see. If we go either way, the y value is going down. Now do keep in mind, once again, just because we have critical numbers does not mean we have a maximum or minimum, but this graph is just a better way of explaining what we did, what we figured out about the graph without actually graphing it until we were done. All right, so that's a good place to stop. In the next video, we will complete this section by showing you how to find the absolute extrema on a closed interval. So I will see you there.